And what does SVD do is the following. If we take our matrix A, represent it exactly as a product of matrices U, sigma, and V transpose. Before we said we can always do this. But now if we want to do dimensionality reduction, which basically means we take U, sigma, and V, but we take part of U and cross it out. We take part of the sigma matrix, cross it out, and we take part of the matrix V transpose and cross it out. So basically now we represented everything instead of using R columns or R rows in V, we represent it using K rows and K columns of V and U. We obtain a new matrix B now that we multiply everything together. And the idea is that B is the best approximation of A. So what by best means is that the Frobenius norm, the difference between A and B, is smallest possible, right? So in a case, A and B are as close to each other as possible, given that we want to represent the data points with a small number of coordinates k. So to be very precise, here is what the theorem says. The theorem says, let's take our input matrix A and do an SVD on it. So it means let's represent it as a product of matrices U, sigma, and V transpose, where sigma is the matrix of singular values that are sorted in the decreasing order. Then let's define this new matrix B that is simply U times S times V transposed, where what is important to note is now that matrix S is simply a diagonal matrix where the first k entries of S are simply the corresponding singular values from matrix sigma, and the rest is 0. So now if we take this new product of, so I have the matrix U, I have the matrix V transpose from before, but now I basically took sigma and changed it into S. Then I obtain this new matrix B, and the idea is that this matrix B is the best reconstruction of A in a sense of the Frobenius norm. So the way I can think of this is the following. So I can think that B is simply a solution to the question, what is the best matrix B that I can find that minimizes the Frobenius norm, where I want the rank of B to be equal to k. So k is the number of dimensions we allow ourselves, the number of coordinates, and what we want to find is the best B that most faithfully represents the data, represents the matrix A. And what do we learn from SVD is that if I'm given matrix A, represented as U, sigma, V transpose, then I want to do dimensionality reduction. All I need to do is cross out a number of singular values, cross out rows in A, and cross out some rows in V. Now I multiply these matrices together, and I'll get a new matrix that is as close to the original one as possible. So the reason why doing this works is the following, right? So what singular value decomposition, it's also called the spectral decomposition of a matrix. And all this says, right, is what we know so far is that we take our original matrix A and represent it as a long and thin matrix U, the diagonal matrix sigma, and the matrix V transpose. So the reason is, why is kind of zeroing out the low singular values, what is the best thing we can do? And the way we can learn this, or at least see why is that a good thing to do, is the following. We basically say, let's take our matrix A that has n rows, m columns, and if we do the spectral decomposition of it, this basically means that we can represent it as a summation of k terms, where we are taking sigma 1, which is the first singular value, the u1, the first left singular vector, times v1 transpose, this is the first right singular vector, and then, plus the second singular value, the second left singular vector, the second right singular vector, and so on and so forth. And as I said before, we are assuming that first we already know that singular values sigma are greater than 0, and we are also assuming now that they are sorted. So, the question is, why is setting small sigmas to 0 the right thing to do? And the way we think about this is the following, right? We already know that vectors ui and vi, they are unit length, right? So because the matrices u and v are column orthonormal, which means that every vector has a unit length. So this basically means that when I take a product of u and v and then multiply that with sigma, basically the sigma scales them, right? So now if I want to have small error, I can kind of drop vectors that have small importance, that basically have small sigma. So this is why zeroing small sigmas actually works and produces the least possible amount of error. And this is kind of an informal argument. We could also give a proof, but this is the intuition why doing dimensionality reduction in a way of setting small sigmas to 0 actually works. So of course, now the question is, how many dimensions to keep, right? So if I take my matrix A, I do its singular value decomposition, and I obtain at the end some R, which is the rank of the matrix singular values and singular vectors, and R in kind of the worst case, the R can be the smallest of M and N, right? Kind of the smallest of the number of columns or rows of matrix A. Then the question is, how many, when I'm doing dimensionality reduction, how many dimensions K should I keep? Or how many singular values sigma should I keep? And the good rule of thumb is that I should keep as many so that I preserve 80 to 90% of the energy. And the way I can do this is the following. Basically, I define the total energy to be the sum of the squares of the singular values. And now what I want to do is I want to ensure that the sum over the singular values I to k, sigma I squared, right? These are the singular values I keep. Dividing this by the sum of singular values I up to r, these are all the singular values I get. I want this ratio to be around 0.8 or 0.9. And this is how many singular values I want to keep, so that I still keep kind of 90% of the energy. Of course, what we also have to talk about is what is the computational complexity of SVD. And to compute SVD, there are standard linear algebra tools, and basically computing SVD in some sense is cubic in the size of the data. So it's the complexity is n times m squared or n times m squared, whichever of the two is less. Right? So in some sense, it's quadratic in the one dimension and linear in the other dimension. So what are the conclusions so far? So what we know so far is the following. We know that we can take any matrix A, any real-valued matrix A, represent it as a product of three special matrices, U, sigma, and V transpose. We know that this decomposition is unique. We know that we can think of matrix U as a user-to-concept matrix. We can think of matrix V as a movie-to-concept matrix. And we can think of the matrix sigma, the singular values, as the strength of each concept. The other thing we learned is how do we do dimensionality reduction. The way we do dimensionality reduction is by simply setting the smallest singular values to 0, which also means that we are kind of removing the corresponding left and right singular vectors to 0. How many dimensions we pick? We pick the enough singular values such that the total energy, that 80 to 90% of all the energy is preserved. Energy defined as being the sum of the squared singular values. And the other thing we saw from the data is that singular value is able basically to pick up or identify linear correlations in the data. So it's able to basically identify dimensions along which the data is spread out the most.